In this video, we're going to go over action potentials. This is going to include a discussion on the refractory period as well as summation. The action potential is the signal that neurons send down their axons to their downstream targets. They can be initiated from signals from presynaptic neurons. As we've discussed, the presynaptic neuron can release neurotransmitters that bind to receptors on the postsynaptic neuron. These receptors can open ion channels that can cause the influx of positive charges. This increases the membrane potential, and we call these increases in membrane potentials excitatory postsynaptic potential. Now usually these excitatory postsynaptic potentials are small, so the membrane potential increases by a little, but nothing much happens. So in order for you to fire an action potential, the membrane potential needs to increase by a pretty good amount to what is called the threshold potential, which for most neurons is about negative 55 millivolts. So if the cell receives enough excitatory input to reach threshold, then the neuron will fire an action potential. And because of the fact that this action potential only fires if threshold is reached, we often call this an all or none mechanism. If the cell reaches threshold, an action potential will be fired. If the cell doesn't reach threshold, then an action potential will not be fired. All right, so now let's look at the action potential in more detail, and we can see this action potential in this diagram. So you can see there are a number of different phases. At the beginning, the cell is at rest, so the membrane potential is the resting membrane potential of about negative 70 millivolts. At the second point, you can see that there is a stimulus, and a number of these stimuli will increase the membrane potential, but they're not enough to reach threshold, so nothing happens. And you can also see in one instance, the stimulus is strong enough to get the membrane potential to the threshold potential. At that point, the cell enters the next step, which is depolarization, where the membrane potential increases significantly to a very positive value. And then afterwards, we reach the fourth step, which is repolarization, where the membrane potential drops and goes towards a negative value. And in the fifth step, we can actually see that the membrane potential drops below the resting membrane potential. And when the membrane potential is below the resting membrane potential, we call that hyperpolarization. And after some amount of time, the membrane potential will recover back to rest. So we're back where we started at the resting membrane potential. So having looked at what an action potential looks like, let's now go through each of these steps in more detail. So to start, we know that our cell is at rest, so the membrane potential is at the resting membrane potential. We know then there are going to be stimuli, and if the stimuli are strong enough to reach threshold, then we'll go into depolarization. During depolarization, when we reach the threshold potential of negative 55 millivolts, we open these voltage-gated sodium channels. When these voltage-gated sodium channels open, now sodium is the most permeable ion across the membrane. And this is going to cause the influx of sodium cations into the cell. This makes the cell more positive, which explains why during depolarization, the membrane potential increases significantly. Now, one thing to note here is that the voltage-gated sodium channels are a big complex. They have two different gates. The gate involved in depolarization is gate M, or the M gate. Now, these sodium channels, when they're open, they actually don't stay open for that long, and that's because they have another gate, the H gate, that will close after some period of time. And this is during repolarization. So during repolarization, the voltage-gated sodium channels will inactivate. And again, this is because the gate H closes. And when gate H closes, this gate cannot be opened by changing the membrane potential. So the sodium channel is inactivated and cannot be opened. At the same time, since the membrane potential has reached a more positive value, this is going to be enough to open voltage-gated potassium channels. and this will cause potassium to rush out of the cell. As potassium rushes out of the cell, this makes the membrane potential more negative. And it actually makes it so negative that it drops below the resting membrane potential, which is our next phase, hyperpolarization. During hyperpolarization, the voltage-gated sodium channel is going to reset back to its initial state, where the H gate is going to open, so the sodium channel is not inactivated anymore, and the M gate closes. So the M gate can be opened by changes in membrane potential. So since this is closed, it is possible to open it by changing the membrane potential. For the H gate, that's not the case. If the H gate is closed, it is closed and cannot be opened. At the same time, during hyperpolarization, your voltage-gated potassium channels are closing, but they close a little slow. So because they close slowly, that's actually why the membrane potential drops below the resting membrane potential and we have hyperpolarization. But eventually, once they close, our membrane potential will be able to recover and return back to the resting membrane potential. Okay, so those are the different steps of the action potential. I now want to discuss the refractory period. The refractory period is essentially looking at periods of time where you either cannot fire an action potential or it is more difficult to fire an action potential. If you take a look at this diagram, you can see that there are two refractory periods, the absolute refractory period and the relative refractory period. The absolute refractory period is called absolute because during the absolute refractory period, it's impossible to generate an action potential. And it's impossible because the H gate is closed and the voltage-gated sodium channels are inactivated. So there's nothing you can do to open voltage-gated sodium channels, so action potentials cannot be fired. The relative refractory period is just after the absolute refractory period, and you can see it's during the period of hyperpolarization. During this period of time, the H gate is open, the M gate is closed. So it's possible to open voltage-gated sodium channels by changing the membrane potential. However, during hyperpolarization, the membrane potential is lower than the value at rest. So as a result, you can fire an action potential, but this requires a stronger stimulus in order to reach threshold. So that's the absolute refractory period and the relative refractory period. So the last thing I want to talk about is summation. As we discussed, when a cell receives an input, that input is often fairly small and isn't going to be enough to get the cell to threshold. So in order to get to threshold, this requires summation. Another thing I want to mention is that when a neuron receives a stimulus or input from neurons, it can be excitatory, which raises the membrane potential, or inhibitory, which decreases the membrane potential. So that means that signals from presynaptic neurons don't always lead to action potentials. They can actually inhibit action potentials. So when the membrane potential increases, that's what is called an EPSP, excitatory postsynaptic potential. When the membrane potential decreases, that's what's called an IPSP, an inhibitory postsynaptic potential. Now, when you want to add up these stimuli, there's two ways that the stimuli can add, through temporal summation and spatial summation. And you can see how that works in this diagram. So you can see at first, if you have an EPSP, then it will raise the membrane potential, but if there's only one EPSP, then it's not enough to get to threshold and nothing happens. So one way you can get to threshold is if you have input from one neuron that fires quickly. So it's sending EPSPs very rapidly. And if they're sent rapidly, then the EPSPs can essentially add. So they add before each EPSP essentially decays away. And that way of reaching threshold by having one input fire action potentials very quickly is called temporal summation. And that can work. Another type of summation is spatial summation. Again, you can see in this diagram, it's possible to reach threshold, but in this case, it's not through input from a single presynaptic neuron. Here you can have input from multiple presynaptic neurons. So instead of having one neuron fire quickly, as in threshold summation, here you can have multiple presynaptic neurons fire simultaneously. And again, if they fire at the same time, then the EPSPs can add up to reach threshold. And in this last part of this diagram, this is looking at EPSPs with IPSPs. So you can see how the EPSP can increase the membrane potential, the IPSP can decrease the membrane potential, and if they're released at the same time, they can cancel out. So again, EPSPs can help bring the membrane to threshold, but IPSPs can prevent that from happening.